So now we get into definitions of acids and bases. So the Arrhenius definition is the first one that we're going to talk about. The Arrhenius definition defines an acid as a substance that produces hydrogen ions in aqueous solution. And the definition of a base, a substance that produces hydroxide ions in aqueous solutions. And whether you recognize the name or not, this is probably the most familiar definition of acid and base. So we see that HCl is an acid because when we put it into water, it ionizes and produces hydrogen ions. It is a covalent compound, but in water it forms ions. And it actually forms ions completely. It ionizes completely. So you put hydrogen chloride into water and it will completely separate into hydrogen ions and chloride ions. Hydrogen ions are very reactive. Let's think about what a hydrogen ion is. How many protons does a hydrogen atom have? 1. And how many electrons? The atom has 1 electron. Are there any neutrons in a hydrogen atom? No. So if we take that hydrogen atom and remove its only electron to make a hydrogen ion, what do we have? A proton. Just a proton. So do you think that's going to be happy just hanging out by itself? No. It's going to be extremely reactive. So we don't actually see hydrogen ions in the solution. Okay? Just like if you go to Disneyland, you don't see 2-month-old babies on the sidewalk by themselves, right? They're too small to be out alone. A hydrogen ion is a bare proton. It's too small to be out alone. So what the hydrogen ion does is we're in aqueous solution. There's water molecules everywhere. Come on, Pointer. And so the hydrogen ion will ride on a water molecule. The water molecule has these 2 lone pairs of electrons. And so this hydrogen ion with no electrons can come in here and form a bond with the oxygen using the 2 electrons from the water molecule. That's called a coordinate bond because the oxygen provides all of the electrons. When we do that, now we have a charge on this molecule, this ion. It's got a +1 charge. And we give this the name hydronium. So it's H3O plus is the hydronium ion. There are other species that exist, but they're much less common. So we tend to use H plus. We tend to use H plus and H3O plus interchangeably because we understand that even if we're writing H plus, we never just have bare protons. It's always riding on a water molecule. It's just easier many times in the formulas to write H plus instead of H3O plus, but they mean exactly the same. Whoops. So a base, well, sodium hydroxide is a base, probably the most common one we deal with in chemistry. And you put sodium hydroxide into water. Sodium hydroxide is a solid. When it's pure, it's soluble in water, and it will dissolve completely. It dissociates. It doesn't ionize. Because sodium hydroxide is ionic. In the solid form, you have ions. So it dissociates, but it produces hydroxide ions in solution. So acids and bases will combine in aqueous solution to neutralize each other. The hydrogen ion from the acid and the hydroxide ion from the water, from the base, will react to form water. And so that should be familiar from previous chemistry classes. Another definition is the Bronsted-Lowry definition. And this applies to more situations than the Arrhenius definition does. This is focusing on the transfer of hydrogen ions. And we just mentioned that a hydrogen ion is a proton. So here the acid is defined as a proton donor a hydrogen ion donor. So an acid is something that loses a hydrogen ion, that loses a proton. A base is something that accepts the proton. So HCl is an acid because it donates a proton to water. So when we put HCl into water, what happens is this proton from the HCl is transferred to the water, forming hydronium ion, and what's left is the chloride ion. So this is clearly describing what happens to the hydrogen ion. It's not actually released in solution, it's transferred to another substance. So this definition also works for bases like NH3, ammonia. Ammonia is a base, but it doesn't have hydroxide ions. So you look at that and you think, well, how could that make hydroxide ions in solution? It doesn't have hydroxide in it. The Bronsted-Lowry definition says this is a base because it accepts a proton. So NH3 in water will take a proton from the water and become ammonium ion, and what's left is hydroxide ion. Because acids are donating protons and bases are accepting protons, those protons have to come from somewhere, right? And so we see that acids and bases always occur together. You can't have an acid donating a proton if there's nothing to accept the proton. So there has to be a base as well. So when we look at this, we recognize that as an acid. We're putting it in water. It forms hydronium ions. But what accepted the proton from the HCl? The water did. The water took the proton. That makes water a base. In this reaction, HCl is the acid, H2O is the base. What's going on up here? The NH3 is donating accepting the proton. Who's donating it? The water molecule. So the water's acting as an acid. Water is amphoteric. So amphoteric, like amphibian creatures that can live on the land and the water, amphoteric substances can act as acids or bases. So water is a pretty cool substance. If we take this chemical reaction that we were looking at ammonia as the reactant. If we write the reaction in the opposite way, we reverse it. Now we have ammonium over here and hydroxide. Well, we can look at ammonium, dang this pointer. We can look at ammonium up there, and here's hydroxide ion, and then we can look at what happens and what they form as products. And we see that the NH4 has lost the hydrogen and that charge, so a hydrogen ion, to become the NH3. It donated a proton. So what's it doing? It's acting as an acid. And what's accepting the hydrogen ion? The hydroxide, right? So now this is acting as the acid. This is acting as the base. Over here, this was acting as the base, and this was acting as the acid. So I did write that, it's just not showing up. So the substance that was the base has become the acid. And that might seem a little confusing. The difference between an acid and a base is who has the proton. The one that has the proton is the acid. The one that's going to take the proton is the base. So in my weird chemistry land, I think of this proton, this hydrogen ion, as being like a young baby, newborn baby, and the baby just gets handed off between people, right? Doesn't ever just get sent out to play. It's like, no, here, you take the baby, I have to go do this. Or at Disneyland, I want to ride the Matterhorn, can you hold the baby, right? So the person who's accepting the baby is the babysitter. Babysitter starts with a B. Base starts with a B. So the base is taking the hydrogen ion, taking the proton. The acid is the one that's donating. And so many substances can act as either. So here we have the acid. It's donating a proton to hydroxide ion, which is acting as a base. After it has donated the hydrogen ion, it becomes a base because now it could take the hydrogen ion back. So what we've got going on here is just handing hydrogen ions back and forth. Any questions? So when ammonia accepts hydrogen ion, it's acting as a base. It becomes ammonium ion, which then can act as an acid. So that's a pair. It's an acid-base pair. They're called a conjugate acid-base pair. So a conjugate acid is a base that has gotten the proton. It's acted as a base, and now it is able to act as an acid. A conjugate base is an acid that has donated its proton. So conjugate acid-base pairs are substances that differ only by a hydrogen ion. So if we look, we've got 3 hydrogens and 0 charge, 4 hydrogens and a +1 charge. The difference between these two formulas is that this one has an H+ and that one doesn't. Over here, H2O and hydroxide ion, H2O has the H+ and the OH- does not. It's a conjugate acid-base pair. You need to be able to identify these conjugate acid-base pairs. So let's practice. In each reaction, identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. So we're throwing these terms around, Bronsted-Lowry and Arrhenius, these different definitions. Is it important in answering this question that it's specifying Bronsted-Lowry acid? Actually, no. The answer's the same, whether you're looking at Arrhenius or Bronsted-Lowry, and so you can just kind of gloss over the Bronsted-Lowry part and say, what's the acid, what's the base, what's the conjugate acid, and what's the conjugate base? So sometimes, we throw Bronsted-Lowry in there and then you freak out because you're like, I can't remember which one that is. It's okay, it's the same answer. So in this equation, chemical reaction, we've got C5H5N. And we're like, what on earth is that? It doesn't matter, we don't need to know. There's water, and over here we have C5H5NH+ and hydroxide ion. So what we're going to do is we're going to identify the pairs of substances, and those are going to be the reactant and product that are most similar to each other. So the C5, this guy, and this one obviously are the closest to each other. And how do they differ? This one has the H+ and that one doesn't. So did this one accept or donate an H+? It accepted it, right? So is that a base or an acid? It's a base. It's like the babysitter. It's taking the baby. So this is acting as a base. After it acts as a base, what does it become? An acid. And so because of what we chose to write as reactants and products, we would call this the conjugate acid, just because it's on the product side. So then what's water doing here? It's acting as the acid because that's where the hydrogen ion came from. So then the hydroxide ion is the conjugate base. Does that make sense? So let's look at this one. Here we have HNO3 and H2O, and we've got H3O+ and NO3-. So which one is the acid here? The HNO3, which, you might kind of guess because hopefully you remember that that's nitric acid, right? So if that's the acid, then water must be the base because you have to have an acid and a base. So then over here, H3O+ is related to the H2O. This is the base, so that's the conjugate acid. I'm tired of writing that word, so I'm going to abbreviate. This is the acid. After it donates its proton, it becomes a base. It could now accept a proton from somebody else. So it's a little bit like a game of hot potato or something. You're just handing this proton off back and forth, back and forth. Any questions?